Welcome to Methods in Biostatistics. Today, we are going to explore one of the most powerful tools in a scientist's toolkit: confidence intervals and levels. Whenever we conduct research, whether we are measuring the wingspan of a bird or the effectiveness of a new medicine, we can never measure every single individual in the world. We have to rely on samples. But how do we know if our sample is actually telling us the truth about the whole population? That is exactly what we will learn today. By the end of this video, you will understand how to measure and express scientific uncertainty with mathematical precision. Let us dive in. To understand why we need confidence intervals, let us start with a simple game. Imagine you are at a fair and you are asked to guess the exact number of jelly beans in a massive glass jar. If you give just one single number, like 542, you are almost certainly going to be wrong. Guessing the exact truth is incredibly difficult. However, if you change your strategy and say, I am highly confident that the number of jelly beans is somewhere between 500 and 600, you are much more likely to be correct. This is the core philosophy behind our topic today. We are moving away from risky single guesses and moving towards safe, calculated ranges. Now that we understand the jelly bean analogy, let us apply this to biostatistics. In biology, we often want to understand a large population, like the average height of all adults in a country. Because we cannot possibly measure everyone, we take a smaller sample and calculate its average. But here is the catch. We know our sample average is not perfectly equal to the whole population's average. There's always some natural variation. Therefore, instead of just giving one single guess based on our sample, we provide a safe, calculated range of numbers where we believe the true average actually lives. This range protects us from being wrong due to random chance. Building on that idea of a calculated range, let us look at the formal definition. A confidence interval, often abbreviated as CI, is a specific range of values calculated from your sample data. Its entire purpose is to capture the true, unknown population parameter. Think of it as attaching a mathematical safety net to your sample's estimate. Because we know our sample might be slightly off from the true population, this interval accounts for that natural random variation. It gives us a lower bound and an upper bound, creating a window where the universal truth is most likely to be found. This brings us to a crucial question. How sure are we about this window? That is where the confidence level comes in. The confidence level is a percentage that tells us how reliable our mathematical process is. For example, a 95% confidence level means that if we were to repeat our sampling process 100 different times, about 95 of those calculated intervals would successfully contain the true population mean. It is very important to note that this does not mean there is a 95% chance that the true mean falls in our specific interval right now. Instead, it means our method of creating the interval is successful 95% of the time. Before we look at the math, let us understand why this matters in the real world of biology and medicine. Making decisions based on a single point estimate can be incredibly dangerous. Imagine a new drug lowers blood pressure by an average of 10 points in a small trial. Doctors need to know if that result is reliable for all future patients. The confidence interval provides a margin of error, showing the best case and worst case scenarios for the drug's true effect. If the interval is very wide, it warns researchers that their estimate is highly uncertain, and they might need a larger sample size before approving the drug. It is the ultimate tool for expressing scientific uncertainty. Now that we understand the concept, Let us look at how we actually calculate this range. The formula you see here builds our interval by starting with our best guess, the sample mean, and then adding and subtracting a margin of error. Let us break down the symbols. CI stands for the confidence interval we are trying to find. The symbol X bar represents the sample mean, which is the average value we actually measured. The symbol Z is the Z-score, a number from a statistical table that corresponds to our chosen confidence level, like 1.96 for 95% confidence. If we want a higher confidence level, this Z value increases, making our interval wider. Looking closer at the second half of our previous equation, we find a very important fraction known as the standard error. This part of the formula explains how spread out our data is and how many subjects we sampled. The symbol S represents the sample standard deviation, which measures how much the individual data points vary from each other. The symbol N is the sample size, meaning the total number of observations we collected. Notice that N is in the denominator. This means that if we increase our sample size, the standard error becomes smaller. A smaller standard error makes our confidence interval narrower and much more precise. Let us put this formula to work with a concrete example. A cardiologist wants to estimate the true average resting heart rate of all marathon runners. She takes a random sample of 36 runners and finds a sample mean of 60 beats per minute, with a standard deviation of 6. She wants a 95% confidence interval, so we use a Z-score of 1.96. First, we calculate the standard error by dividing the standard deviation, 6, by the square root of the sample size, which is also 6. This gives a standard error of exactly 1. Next, we multiply this by our Z-score to get a margin of error of 1.96. Finally, we add and subtract this from our mean of 60. We can now confidently state that the true average heart rate is between 58.04 and 61.96 beats per minute. Having successfully calculated a 95% interval, you might wonder what happens if we want to be even more certain. Sometimes, especially in medicine, we need to be absolutely sure about our estimates. If we increase our confidence level from 95% to 99%, we must use a larger Z-score. Mathematically, multiplying by a larger Z-score increases our margin of error. This means our final confidence interval will be wider. It makes intuitive sense. If you want to be more confident that you have captured the true population parameter, you need to cast a wider net. Let us see how this plays out in another example. Following up on that idea, let us look at a pediatrician studying the birth weights of newborn babies. He samples 100 babies and finds a mean of 3.2 kilograms with a standard deviation of 0.5. Because he wants 99% confidence, we use a larger Z-score of 2.576. First, we find the standard error. Dividing 0.5 by the square root of 100 gives a very small standard error of 0.05. The large sample size really helped shrink this. Next, we multiply by our new Z-score to get a margin of error of 0.1288. Adding and subtracting this from our mean, the pediatrician can conclude with 99% confidence that the true average birth weight falls between 3.07 and 3.33 kilograms. To truly cement this concept, let us visualize what we have been calculating. Here, you see a standard normal distribution curve. Right in the middle, at the highest peak, is our sample mean. This is our best single guess. Stretching out to the left and right from that center line is our margin of error. Together, they form the central unshaded region, which represents our 95% confidence level. The shaded tails on the far left and far right represent the remaining 5% of probability, split into 2.5% on each side. This diagram beautifully shows how the confidence interval acts as a mathematical net centered on our sample, designed to catch the true population parameter. We have covered a lot of ground today, so let us summarize the most important ideas. First, remember that confidence intervals bridge the gap between limited sample data and the universal truth of a population. They provide a calculated range of plausible values rather than a risky single guess. Second, the confidence level tells us how often this mathematical net successfully catches the true value over many repeated experiments. Finally, we saw the trade-offs. Increasing your sample size gives you a narrower, more precise interval, while demanding a higher confidence level forces you to create a wider interval. By mastering these concepts, you are now equipped to make safe, informed decisions in biostatistics without being misled by random variation. Great work today.